Aloha, everyone. This is Ziyu from Snapchat Research. I'm presenting our paper titled Creativity Generating Diverse Questions Using Variational Autoencoders. This is a joint work with Unnat and Alex from UIUC. Equipping AI agents with creativity is an important problem for many tasks where results are ambiguous, such as making a spotlight presentation or the task we address, that is, asking questions about an image. For this task, given the image shown on the slide, we want a framework to propose a diverse set of questions, ranging from literal ones, such as is there a candle burning, to inferential ones, such as is this a formal occasion. So classic techniques sample diverse results by first extracting an image representation, then estimating a probability distribution over questions, and finally, either extracting the highest scoring questions, which will be very similar, or extracting modes, which will be computationally expensive. In contrast, we propose to sample from a simple distribution and subsequently transform the samples via function approximators, such as deep nets. Towards this end, we employ variational autoencoders to model the distribution over questions. Variational autoencoders assume that each data point x is generated from a low-dimensional representation z. During inference, we first sample z from a prior distribution and then generate a data point x with a deep net. So how do we train this process? Given a set of samples x, we want to maximize the data log likelihood. By introducing a variational posterior Q, we can lower bound the data log likelihood via a KL divergence between Q and prior over Z, as well as the expectation of the log conditional probability Px given Z over Q. More specifically, to compute the objective function, we use data X, in our case, training questions and image features, to compute the variational posterior Q, also known as the encoder. Upon drawing sample Z using the mean and variance from the encoder, we can approximate the expectation by evaluating the log conditional probability via the decoder. It remains to answer how the decoder and the encoder look like. Since we deal with texture data, that is questions, we employ a long short-term memory network as our encoder. We feed image features and trainable word representations into the network and collect the mean and variance upon completing last step of the LSTM. The decoder is also based on an LSTM network. We feed image features, latent variable z from the encoder, and trainable word representations into the network, and obtain word probabilities for the next word from each LSTM step. So how well does all this work? To train our model, we combine the mighty VQA dataset with the recently proposed VQG dataset. Let's take a look at some of the generated questions. Note that questions with a tick to the left never appear in the training set. Hence, our model not only chooses the most relevant questions, but also generate new ones. Of course, our model also makes interesting mistakes. For example, there are recognition-based failures and co-occurrence-based issues illustrated in the right two figures. Mahalo. Please check out our poster for more details. Our post number is 8.